All right, good evening, everyone. I hope this finds you very well. So this video is kind of tailored towards approaches on how to answer your R and S chemistry questions. In all honesty, this is going to be a pretty hard topic. You'll need a lot of spatial imagination. If you don't have very good spatial imagination, then you're just gonna have to like keep practicing because in all honesty, you just have to keep practicing. There's no way around. I'll show you tricks on how to remember it, but for me personally, when I was taking this, this was probably the hardest thing for me to grasp my head around. I with time, I eventually got it. I think the Sunday before the test, I just like sat down, just did a bunch of the stereochem, and I finally got it. So I highly recommend, this OChem. You have to put a lot of time into it in order to get it. You can't half-ass this part of OChem. This is half of the or a good chunk of the exam this coming Friday for you guys. All right. Well, that being said, let's go ahead and we'll jump into it. There we go. All right, you guys should be. There we go. All right, you guys should see my screen right now. All right. Now, the first thing for stereochemistry is identifying a chiral center. What is a chiral center? A chiral center is an sp3 hybridized carbon with 4 different branches on all 4. Because if you know from class, if you have different arrangements for an sp3 hybridized carbon, there's different arrangements so they're not superimposable. That's the definition. Chiral means they're not superimposable. They're handedness. Right hand or my right hand, left hand, they look pretty much the same, but they're not superimposable. Of course, you can flip like this. That's not the same, right? Your hands are enantiomers, but we'll get to that later. Now, for sp3 or for chiral carbons, 1, they're sp3. 2, all 4 carbons or all 4 branches are different. And we assign priority 1, 2, 3, and 4. Okay. Now, ones that have hydrogen, a hydrogen atom is the smallest priority. It's the smallest atom we can have. It's literally a proton and obviously that sigma bond with a chiral carbon. Okay. So if you have hydrogen, that's pretty much going to be your fourth priority. But let's say, all right, this is number 4. You had 1, 2, and 3. We're going to try some stuff out later on, but for now, just 1, 2, and 3. Well, the way we tell it is if it's counterclockwise, it's S. If it was clockwise, it's R. And how I usually think of it is when I write out S, I start off that first curve clockwise or counterclockwise when I'm drawing it out. And then for R, when I draw out that big curve for R, I go clockwise. That's how I like to imagine it. Now, some distinctions I want to make. What's not a chiral center? All right. What's not a chiral center? sp2 hybridized carbons. If it's sp2, it's planar. You have E or Z, not R or S. All right. There's still a stereochemistry because those sp2 carbons cannot rotate. There's no free rotation, but there's still E or Z, cis or trans. And the next biggest thing is carbons with identical groups. The moment you have 2 out of the 4 branches become or the same compound or the same like chemical formula, like CH3 and CH3, it's no longer chiral. It's achiral. It's symmetrical. So right here, these are the same line of symmetry. There you go. In this case, they're R's, but it's the fact that 2 of those bonds are the same. The moment 2 of them are the same, you have a line of symmetry. All right. Now, for going for chirality, actually, let's go ahead and just start with some practice. So right here, we're going to start off plain and simple with what I just said. Okay. Is this carbon a chiral carbon? No, it's not. Because if you look right here, CH3, CH3, they're the same thing. They don't need R or S because this carbon is achiral. Now, what about this one? Is this chiral carbon R or S? Well, I'm going to show you a neat little trick when it comes to counting clockwise or counterclockwise. Your 4th priority group should always be in the back. As in, when you count it clockwise or counterclockwise, you have to do it as if the fourth group is in the back. So if this was your sp3 hybridized carbon, right? Let's say white was the hydrogen. And whatever these were, let's just say I assigned these the OH, I, and the BR. What you're supposed to do, and what Gavin likes to say, you basically grasp it by the hydrogen and you look down the barrel. All right. So by having the hydrogen or the fourth group pointing away from you, you can accurately read clockwise or counterclockwise. And we'll see this in action right now. So if we prioritize this, remember, atomic size, iodine is the biggest, then bromine, then OH, or the oxygen OH. All right, 1, 2, 3, and we already identified H as 4. All right, we don't have to do anything. H is in the back, so we can just count it normally. 1, 2, and 3. That's counterclockwise. So this would be S. All right, and it's S because we counted it while the H was in the back. All right, let's give it one more shot. All right, so you have this chiral carbon. Okay, now let's assign our priority chart. So we already know, okay, out of carbon, chlorine, hydrogen, chlorine is the highest priority, 1. Hydrogen is the 4th priority, 4. Okay, now it comes to ethyl or a tert-butyl group. Well, this is some stuff that some people might still have some trouble on in regards to E or Z, but draw out your carbon where it's connected to. All right, that carbon, if I were to expand it, all right, I'm supposed to be like, I don't know how to show that, but this carbon right here, I'm just going to expand it. All right, this carbon is that carbon. I'm just trying to represent it. Carbon, carbon, carbon for those CH3s. So this carbon is connected to 1, 2, 3. 3 carbons. This carbon is connected to 2 H's and then this methyl group. Right? C versus just 1C. Which one is bigger? It's going to be this one, 2 and 3. All right. So now that we have assigned our priority, let's go ahead and count. All right. 1, 2, 3. We're going clockwise, and that's R. Now, our 4th priority group is in the back. It's dashed. It's facing into the page, not looking at us. So we keep it. And this is where the switch method comes in. This is the switch method. All right. Look over here. Hydrogen is in the front. So keep that in mind as we're going to work through this. So let's go ahead and assign our priorities. Which one's the biggest one? Well, bromine is the biggest one, biggest atomic number. And there's chlorine, 2, oxygen, 3, and hydrogen, 4. Let's look at the stereochemistry video. Let's look at the stereochemistry. All right. 1, 2 to 3. 1, 2 to 3 is counterclockwise S. Normally it would be S, but notice, look here. H is in the front. H is in the front, meaning that we have to switch it. That's an easy way. Just the moment the fourth group is in the front, switch it. It's going to be R. And you might be thinking, why? Well, you can get by just knowing, all right, if H is not in the back, I have to switch it. But just to go to show, this is what you're looking at the page, right? So, sorry, that's my cat. H is facing in front. H is facing in front, right? He's facing towards you, right? Well, if I'm counting it normally, well, the moment, or that's my perspective, but when you're looking at your perspective, you flip that entire rotation. That's why I switch method, because you're counting. When you count around, 1, 2, and 3, H is in the back. So if it's in the front, you're reversing that entire process. So if H is in the front, switch it. Okay. This might come in handy when we're doing Fisher projections. Okay. What if you had a double bond? This is in some of your problem sets, right? What if you had a branch that was a double bond? Let's say C. H, we'll make it easy. H. C double bonded. CH2, CH3, OH. Let's assign our priorities. We know that hydrogen, fourth priority, oxygen, first priority, because we're looking at atomic mass. What's bigger, oxygen, carbon, or hydrogen? Oxygen. Which one's the smallest? Hydrogen. Now we're looking at, let's make it a little wackier. Now look at this. Look, they have carbons there. Which one do we look at? Well, look at the connectivity. A double bond counts as 2 carbon-carbon bonds. I'm going to repeat myself. A double bond counts as 2 bonds, all right, because you're looking at connectivity. So if this carbon is connected to hydrogen, 2 carbons, quote, 2, because those 2 bonds represent the double bond. This carbon is connected to 2 hydrogens and 1 carbon. Which one takes priority? It's going to be this top one. All right. And if you think about it, alkenes take priority in naming. They take priority here. There's more carbon-carbon bonds. All right. Don't ask why, is because. Okay. More carbon-carbon bonds. So let's look at the priority, or let's look at the stereochemistry. 1 to 2 to 3. That is clockwise. That's R. And just to double check, is our 4th priority group in the back? Yes. So do we need to change it? No, we do not. Okay. Now let's take a look at actual structures. And this is very important for the test because it's not like you'll have an entire page dedicated to some test. But yeah. Okay. Well, for chiral, just the definition means not superimposable. Another definition, no internal, or just no line of symmetry in general, no line of symmetry. Achiral, superimposable, plus internal line of symmetry. All right. So when we're looking at any line of symmetry, we're looking at just something that can cut through the molecule and it's equal both ways around. And we'll see some examples, don't worry. But another word you might see is mesocompound. Now, mesocompound is an achiral molecule, or just basically a molecule with 2 stereocenters that has an internal line of symmetry. We will see an example of this. I will show you what this is, but just keep in mind, a mesocompound is a 2+ chiral molecule that has an chiral center molecule that has an internal line of symmetry. Again, I'll show you what it is. So let's move on. So the first kind of structure that we'll be looking at are cyclic structures and chair conformations. This personally is one of the easier ones because probably the hardest one is Fisher projections, and maybe Newman projections might be a little mid. This one is a little easy. So just to clarify, anything on that line of symmetry is fair game. And you'll see why in a minute, but I just want to prime your head, get you thinking a little bit. So if you have, let's say, a plane of symmetry, and let's just say it's on one single atom, okay? Let's say you have like a big iodine. If you were to hypothetically cut through it, there's an internal line of symmetry because that atom's the same. So with that logic, anything on that line of symmetry does not have to play in the symmetry, if that makes sense. You'll see what I'm talking about in just a few seconds. I just want to prime your head. All right, anything that lies on the plane of symmetry is fair game. So if you're looking at this right here, is this chiral or achiral? Does it have a line of symmetry? And your brain might be thinking, well, if I go this way, that's not symmetrical. If I go this way, that's not symmetrical, nor this way, that's not symmetrical, which you're right. But if you were to cut it down here, that's symmetrical. And you might be thinking, what? They're different directions. One's up, one's down. One is bromine, one is chlorine, right? But when it's written like this, it's planar. And let's just say you're looking at the side view of that cyclohexane. All right, this is the side view. You know, your bromine is facing up, your chlorine is facing down. Well, that line of symmetry just cut through the entire thing like a little, I like to imagine a glass slide just slicing through it. Those two halves are symmetrical because the bromine and the chlorine atoms are in that line of symmetry. So they're also cut in half. So you don't have to worry about these being symmetrical because you're not comparing the line of symmetry this way. All right. You're comparing it this way. If we're looking at it there, two hydrogens, right? Obviously symmetrical. And you have your half of ring structures. That's symmetrical. All right. So let's just take a step back. All right. I know I just shoved a bunch of info at you, and some of it might be like, wait, what? Which is understandable. This is organic chemistry. It's organic chemistry. Of course, it's going to be difficult. All right. But look, line of symmetry right down here. If the atoms lie on that plane, it's fair game. It's fine. So this has an internal line of symmetry. So this is achiral. Let's start poking at some other examples. See if we can get the ball rolling. Okay. Look at this one. Is this chiral or achiral? Does it have an internal line of symmetry? Well, let's take a look at some possible ones. So let me redraw this cyclohexane a little more pretty. So if we were to draw that line of symmetry down here, is that symmetrical? No. This has a methyl group. This does not. Okay. What if we were to draw it down here? Same reason. No. Methyl group, no methyl group. Okay. Well, what if we were to do it down here? Ooh. Ooh. That looks pretty symmetrical to me. So I'm going to say that's achiral. All right. Now, let's start poking some fun at, oh, wait, no, here's another example. Internal line of symmetry right here. So this is achiral, line of symmetry. This one, same reason. Down here, no line of symmetry. Here, that's not a line of symmetry. Here, the same route we went up there. Nah, this is pointing away. This is pointing towards you. You might be thinking, didn't we just do that 2 compounds ago up here? We did, but they lie. Yeah, they're on that line of symmetry. Okay. These groups don't lie on that line of symmetry. So they're not fair game. We have to consider their spatial arrangement. And if you're looking at this, these are chiral. Okay. All right. For this one, you have a chair conformation. What do? It's not, you can't just slice it in half because it flip-flops around. What do? Well, undo it. You undo that chair conformation. So if I were to undo it, I would make a cyclohexane. Okay. This is up, this is down. So up, down, CH3, CH3. That's what we saw. All right. That's what we saw. So we already know that's not achiral. There's no internal line of symmetry. That's chiral. Okay. I'm gonna get a little water break. Let me stop share. Let me pause this real quick. All right, I'm back. This is my cat. This is Sugar, one that was making noise earlier. Okay, I'll let you go. Okay, back to the video. Okay, so back to where we were. This No plane of symmetry. It is chiral. Now let's take a look at this one. All right. Chair conformation. What do? Make it a planar. Okay. This is up. This is up. BR. BR. And it's on the 1 and 3 carbons. 1, 2, 3. 1, 2, 3. Okay. That's how I made that. All right. Is there an internal line of symmetry? Here? Nope. Here? Nope. Here? That looks pretty symmetrical to me. Look at both sides. All right. So if we're, let me make this a little neater. 1 carbon down from that line of symmetry, you got chiral carbons. They have BRs and they're facing into it or facing us. They're coming out of the pitch. So that's a plane of symmetry. The spatial arrangement is the same on both sides of that line. The groups are the same. So this is achiral. There you go. Okay. Now let's take a look at some Newton projections. Now this one, it's easy to wrap your head around. The key to solving if this is chiral or achiral, you literally just spin them. You align them together so that they're eclipsed. I'm going to repeat that. You just rotate them so they're eclipsed. That's it. Okay. So this bromine and this bromine, well, let's look at this structure. Let's look at this as a whole. Okay. It's in a staggered formation. How can we tell that there's a line of symmetry? Not the brightest idea to do this off the bat. And what I'm talking about is don't just draw lines willy-nilly, like line of symmetry. Not the best idea. Okay, you have to align them and then take a look for yourself. So let's run it back. These BRs, let's start rotating them 60 degrees so that they're aligned. So BR, these H's, H. Okay, sorry about that. Okay. Okay. This is the process of rotating it. Let me bring this back to green. Those CH3s will be right here. And you see, this is like that little weird transition as I'm like turning it. You see, like this bromine moving over as I'm moving it closer and closer to align with that. This is what it is. Okay. So let's just redraw it. BR. And in actuality, they are eclipsed, but I'm just drawing them a little inch away from each other just so that you guys can see it. All right. Now this part is really easy. Every single group matches. If they match, it's achiral. That's it. All right. Now let's give it another shot without this one. All right. So BRs, I'm moving one closer to that other BR. All right. This H, I can't completely just rotate it over there. You can't do that because I'm only moving it 60 degrees. So I have to make that H eclipse over here. So it's going to be H, CH3. And then this CH3, 60 degrees, that H. Okay. Now let's look at the groups. BR, H, CH3, and then H, CH3. Now look at these. Matching, not matching. So is it chiral? No. Or wait, is it achiral? No. Is it chiral? Yes. Chiral. They're different. Now you might be thinking, well, why don't you just rotate the other groups, right? Let's instead of the bromine, let's rotate that hydrogen over here. Well, if you did that, which is plausible, you rotate it 180 degrees. That means this would rotate 180 degrees and eclipse with that bromine, and that bromine would eclipse over here. There's still no matching. All right. So there we go. Okay. So some dead giveaways if it's chiral or achiral. The first thing, you have groups that are not the same. So look at this first one. Okay, that hypothetical chiral carbon, I mean it's chiral, but that carbon that is connected to a CH3, that back carbon, which is connected to bromine and chlorine, a bromine and a hydrogen. Okay, it's connected to four different things. And the back carbon is connected to CH3, Br, Cl, and this front carbon. Well, look, there's a difference. Cl in one carbon, but this carbon right here doesn't have any Cls at all. There's no Cls. So is there a line of symmetry? Nope. There is no line of symmetry. They're different. Okay. For the second one, okay. Look at this front carbon. Is it chiral or achiral? Well, look at this one. You have two groups that are the same. So that front carbon's achiral. But it might trick you because look, you still have that back carbon. And that back carbon is connected to a Cl, a Br, an H, and a carbon. That back carbon still has four different groups. So that's still chiral. All right. And if you're to move around, you can obviously see none of those groups are the same. If you were to eclipse it, they don't even match up. So that's pretty easy. That's going to be pretty chiral. All right. Now let's look into the hard ones. Fisher projection.